Okay, so I'm happy to start on time and to welcome all of you to the 2026 summer school of AI for pathology. I'm very happy to do that. I think already for the fifth or sixth time. And well, I'm actually using the same slides, but I really have to update them each and every year. I think that this year the updates are really significant comparing to the gaps that I experienced in the previous years. I really, it's amazing, I think, to see what has happened in AI in general and in AI for pathology in particular in the last 2 years. Since I'm working in this field for the last 10 years, I really can feel that things that we struggled for and really fought 3, 4 years ago, things which were really, really difficult and time consuming, nowadays are easier and quicker to achieve. So the revolution still goes on. But we start from the very beginning. So let me share my slides and we kick off the session. I also wanted to record it. So just one moment. Where do I record? Record. Okay. So, I think, it is recording. Okay, cool. So recording was done automatically. This is thanks to Masha, of course. Okay, so let me share my screen and we kick off with the session. Okay, so I hope, let me just go to slideshow mode. Okay, so we are in the AI for pathologists course. This is a course that is provided to the community as a service. Just for disclosure, I have 3 main reasons to do that. First of all, I'm a person who loves to be a part of a community. So doing things for the community are important to me. So this is reason number one. Reason number two, when I give webinars or such a course, I need to learn. I love learning. It also keeps my brain alive and kicking. So this is reason number two. And the third reason, I'm co-founder and co-CEO of DeePathology. We are active in this field, and I sincerely believe in I would call it intelligent marketing. And this is why this AI for pathologists summer school will be composed of 7 lectures, which will be completely educational, no marketing free, and the 8th and the last session would revolve around our platform, the DeePathology Studio. We are a commercial company, and of course, we need to also sell our product, but we will have a dedicated session for that, where we will discuss our DeePathology Studio. So I'm Chen, just a quick background. I have a PhD in applied mathematics, specialized in computer vision. I did my PhD before the AI revolution, so I completed it in 2005. Worked for some years as algorithms developer, and also had the privilege to do my postdoc in the University of Bremen in Germany. In 2009, I started my entrepreneurship path, co-founded SagivTech together with Nitzan, my partner for business and for life. And in 2018, co-founded DeePathology, and our main product there is the studio, a do-it-yourself platform that brings AI immediately to the hands of pathologists. So this is me. What can you expect from these sessions? So today we are going to talk about the basics of deep learning. Also, the next session will be dealing with classical deep learning models. And then in August 11th, it will be a very important date in our course because we will go through the revolution that happened in AI in deep learning. We will discuss transformers and large language models. These are the building blocks of foundation models, which are now super important in pathology. Then we will have a session dedicated to agentic AI, which is really already revolutionizing, but I think still has to bring its full impact to pathology. Then we will have two sessions really dedicated to a lot of, I would say, several, I would say, studies that deal with AI in pathology, reviewing what happened in the last decade, but also looking at state-of-the-art happening today. And then 2 months from now, we will have the DeePathology Studio live demo, also showcasing, I would say, some exciting new features from the world of foundation models, agentic AI, etc. Because I can tell you one thing, after being almost 18 years an entrepreneur, if you want to at least stay in one place, you better run super fast. So we will go over all of these things, but please, this course will not make you an AI expert. I love mathematics, but we will not dwell into the mathematical details in this course, and it will also not be a course that will teach you how to program. These are all very important things, but we will not do this here. So the structure, as you've seen, 8 lectures every Tuesday. The very last lecture will be like a week, 2 weeks, I think, after the 7th one. You can join any lecture that you like, of course, and you will have full access to the recordings. And now, I know this is in the structure of a webinar, but I love to talk. I can talk for hours, but I also love to listen. So any questions will be appreciated, both online and also offline. You are very welcome to email me, chen@deepathology.ai. I will also, in the after each lecture, you will have like a summary email with all the information. So you will also have my direct email in case you have any question about the course. I will try to answer, of course. So enough with the personal introduction and also the introduction for the course. Let's get started. And the aim for this talk would be for you to understand the basic building blocks of deep learning, deep neural networks, and also get an idea of how they work. And this is really super important because nowadays we have very, very complex, huge AI structures, but they all are beginning with the basics. And, you know, like in mathematics, you start with 1 + 1 = 2, and then you have like huge theories. So it's the same here. So AI really seems to be everywhere. I mean, it's unbelievable. This statement is only becoming more accurate from year to year. So yes, we do have some places where you can hop into a self-driving taxi, but still you see a lot of drivers in the roads. And for example, myself, I love to drive a car which is manual and not automatic. I can share with you that my fantasy is to have a 4x4 Fiat Panda. It's really a very, very special car for me. But I don't think they will have a self-driving Panda. Let's see. I think one of the cornerstone works in AI for healthcare was when Google's breast cancer screening AI proved to be better than radiologists. And this is really amazing what you see. I think radiology is really, I would say, is super, super advanced in foundation models, in applicability, in practice, because, you know, X-ray went digital a very long time ago. Whereas in pathology, we still struggle. We still have to overcome the gap of becoming digital. But I think that the potential was already seen with classical algorithms already a few years back. So AI is transforming not only I would say a code generation and automating of call centers, but it's also really revolutionizing healthcare. ChatGPT, Gemini, Claude, all of these tools have become a part of our lives. So you know, it's like let my ChatGPT talk to your ChatGPT, and they agree on things, and we just are, you know, bystanders. And I think it raises so many issues and questions when it comes to studying at universities, expressing yourself. I mean, remaining innovative and keeping critical thinking. These are all super important. And I think that we all, as individuals and as communities, have to learn to use AI because it's amazing on one hand, and keep our, I would say, the spark that makes us human on the other hand. So in this course, we will first focus on this stage, what I call the classical deep learning. Classical deep learning means that we talk about supervised computational neural networks that are trained to really solve very specific tasks. So this is, I would say, what has happened since 2012 until probably for a decade. And then transformers and foundation models came along, self-supervised, huge models that are able to learn representations of images, of sounds, of texts. So really ability to capture and understand the structure of several domains. And also, I would say, and then how to integrate all of these into agentic deep learning ecosystems where the role of AI is not passive anymore, but is active. And we are building our agents like little helpers that can really assist us. And now, you know, in the entrepreneurship, there are the super founders where you have like a founder, which is able to create like all of these agents for marketing, for R&D, for reaching new customers. And these are tools that we have to know how to master, because it will give us power to do more efficiently, and hopefully give us some more time to relax. So when we talk about state-of-the-art in AI today, then we are looking at multimodal frontiers, and this is also super relevant in medicine, because if nowadays you have solutions for radiology, you have solutions for pathology, you have solutions for cytology, etc., MRI, then at some point you want to have like one entity, one AI entity, which will try to dictate things and to come to conclusions from looking at the entire data and not only some kind of projection of the data. Then agentic workflows are really, I think, super buzzy nowadays, and foundation models. And all of this is true for general AI, AI in healthcare, and definitely AI in pathology. So I would say that in the last 2 years, you can see two super important trends in computational pathology. One is having agentic AI, and this can come starting from natural language intent, which means that if like up until now, when you use tools such as RStudio and you have to really annotate the yellow cells, what we have now is you ask the system or you type annotate the yellow cells. So this is like some kind of a higher level or a higher way of interaction with AI systems. Autonomous planning. So it means that if you have some kind of a workflow, and a workflow is very, very common in medical care, in pathology, in cytology, in research and diagnostics, then once you have an agent, you can decompose tasks which you had to do manually, and at least some of them, or you can supervise the process, but still some of these tedious tasks can be actually become autonomous. And this is another thing which is happening right now. And agents can also be used to do refinement of results either in research or in diagnostics, which means that I strongly believe in having the human as the decision maker. And all of these agents would be, I would say, data collectors, data annotators. They will work on optimize things, but to have an agent that can actually consult with you, come back to you as the user, as the decision maker, and have some kind of a ping pong and interaction between the agent and the experts. I believe in this approach, and I think that a lot of systems are also taking this direction. Another amazing revolution in pathology was the usage and development of foundation models. I believe that it all started from usual computer vision, where companies such as Meta released their Dino or SAM3 foundation modules which are trained on a huge number of natural images. You take these models and you retrain them on huge number of pathology slides, and then you have the capability to extract information, to extract what we call the embedding space, the feature space from all of this information. And this embedding space can serve for several tasks. So you have your slides and you have some kind of a foundation model. The foundation model extracts, gives you some kind of a representation, and you can use this representation to solve a lot of problems. And this is really a paradigm shift that we see in AI today, and we will go through this paradigm shift in this course. But let's start from the beginning, because as a mathematician, I believe in always start from step one. So now we talk about digital pathology and AI. These are really game changers, because what pathologists did for 150, 160 years, look at the pathology slides. Once you had scanners which had resolution good enough to show the slide, the contents of the slide on the screen and not lose any information. Once we, as mathematicians, as AI developers, once we have the slide as a digital file, we are happy because we can apply algorithms to this slide. So becoming digital is an enabler for this process. And it is important to understand that because when you want to have the AI revolution, you have to make this jump and become digital. It's in some countries, in some places, it's very trivial. It costs a lot of money. So this is why the revolution really takes its time, because it takes money and resources to build I would say, the infrastructure to enable AI in research and in diagnosis. So pathologists definitely, I would say, want to use AI in diagnostics. You don't want to spend your life searching for Helicobacter pylori. You don't want to count the black dots in the pink stains. Okay, this is, I mean, it can be very relaxing, but I guess that pathologists can do better usage of their times. Also for pharma research, you want to take advantage of AI because you want to be able to predict things. So many things. I mean, you want to take some gut feeling and transform it into quantitative analysis. And this is also true for preclinical trials, for disease research, and for biology research. And in the last decade that I'm working in computational pathology, I came to get familiar with a lot of research done in universities all around the world. And I think that it is really amazing, the synergy between people coming from the clinical aspects, coming from the AI aspects, how they actually work together. And I believe that I, as a researcher from the AI side, I really need to understand a little bit of the clinical and the pathology side. I believe that also pathologists are also interested to be more than just, users of AI, but really to understand what's inside this black box in two ways. One is to understand how it's working without solving equations, and maybe writing scripts in Python. Although I know a lot of pathologists and biologists who actually do that, and very well, by the way. But also to be able to understand the results that they obtain so that they will be able to judge the quality, and I would say the robustness and how trustworthy are these results. And I think that this is super important. So when we talk about digitation as an enabler, we want to have scanners which work at least as good as microscopes. And this was like a big deal of an issue, I would say 7, 8, 9 years ago. But also the evolution in scanners has been tremendous. And I think that the resolution that they offer nowadays is absolutely amazing. So we have, so our starting point is a digital file, and we want to analyze it. So I'm now taking you back to the years before 2010, 2012, where the community of image analysis was really dealing with classical computer vision. And in classical computer vision, let's say that you wanted to count the number of red circles here. So as a classical computer vision person, I would say, okay, my task would be to find these red circles. So I have some hints, I have some features. I'm looking for red pixels. I'm looking for a round shape. So let's design filters. Let's design ways to detect these circles, relying on the features. So the task of computer scientists and researchers back then was to really understand the type of features which are relevant to each and every task. And this was our work, because then we have tools, we had filters, we had convolutions, we had the thresholding, we had a lot of I would say ways to do that, and we had to understand and to figure out what we actually had to do. And this is a simple problem, and sometimes we would have more complicated problems. And this is not really a complicated problem, but it's more complicated than the previous one. So here we had to think a little bit harder and say, it's not okay. It's not only the color. We have also to account for the for the shade of red, and we also have to account for the size. So we had more features, and we had more, I would say, use cases and more things to consider, and we had to develop more complex methods. But still, we needed to understand what kind of features will make a difference here, and then we can classify, and then we can detect, etc. And this is like a novel way of classical machine learning. And you see that this work was also, I mean, 8 years ago. So it's really, I would say, the very beginning of AI in pathology. But then you take an whole slide image. You usually have to look at tiles because the whole slide images are really, really huge. You are trying to extract features in some ways, so texture, color, size, whatever, and we as computer scientists would design filters to do that, and then arrange these features and try to figure out what these features can tell us in order to segment tissues, find cells, etc. So this was like classical way of working. And after we figured out the features, we would try to separate the features and figure out what's going on. In classical computer vision, I can tell you from experience that we had a lot of glass ceilings where we couldn't figure out what to do. So in cases like that, where we had case A, case B, you could actually put some line to divide, and you had an excellent way. And these methods, by the way, still work fantastically. Okay, they work well. But sometimes the methods were not enough. I mean, you couldn't find a decent way to differentiate between, let's say, two groups, necrosis and stroma, for example, based on features. It was overlapping, it was mixing. You couldn't figure out the features that will make the separation clear. And we were stuck for several years. And then came along deep neural networks. And this is the first paradigm shift that we are going to talk about in this course. And the paradigm shift is moving from classical machine learning to deep learning. And the main difference would be that if in classical machine learning, we had to handcraft the features, the feature extraction process, and then train some kind of a classifier that would differentiate necrosis and stroma. In deep learning, these two are integrated into a single process, which is done by the neural network. So the extraction of features and the classification are being done simultaneously by the neural network. And then a lot of people thought that the role of computer vision developers would, stop to exist, and everybody panicked. I mean, so panic is becoming really a part of our life since the AI arrived. But I think that we have learned that good computer vision developers are a must for having good algorithms, because they have to know which tools to use, which architectures, how to combine things together, and how to make things work. So the role of computer scientists and computer vision researchers definitely changed because the set of tools has changed. And I believe that this is a change that many industries and many professionals are experiencing, including pathologists, because a pathologist could use set of tools which can really make his or her life easier and better. So this is the first paradigm shift, going from manual features extraction and then training a classifier to a neural network that does these two things together. So what are neural networks? So deep neural networks are really a lot of mathematical operators, which are some kind of a network, okay, where you have an input and you have an output. Here, the input is some kind of a whole slide image, and the output would be a segmentation mask, okay, to segment it. So we take the input, we start doing an operation that is called convolution. I will go over all of this in a minute. So these convolutions are producing what we call features maps, and this process repeats again and again and again and again and again. It can repeat a lot of times. We call this, the number of times that this is happening, the depth of the neural network. So when a neural network has like 3, 4, 5 layers, then it's not deep. It's a shallow neural network. And in the very beginning, like there were really shallow neural networks, and they started to become really bigger and bigger and bigger. So we have here extraction of feature maps. And you see that these feature maps are becoming smaller and smaller. Why is that? 2 reasons. One, to make the computational burden easier. And the second is because we analyze the information in a multi-scale way. Okay, so this multi-scale way means that we are looking at the information at several scales. And so we want to look at it at very, very fine scale, at a pixel level, but we can also look at it at larger and larger areas, because also when we look at the world, we are able to focus on very small details, but also have some kind of an overview. Our eyes, by the way, are built to actually do that with the roads and the cones, to have a focused vision and also have to give us some kind of, the background. And finally, we have here what is called a fully connected layer. So like a vector with a lot of numbers. And so just imagine like a vector with a lot of numbers. Each of these numbers is weighted to create some kind of an output. Okay. And so we have some kind of a weighted average in a way to provide an output. And this output can be a segmentation map, it can be a classification, it can be detecting of object, it can be a decision of survive, did not survive, this drug worked, this drug did not work. You can predict from age and E the genomic structure of a person. Okay, so what you can predict from a neural network depends on the data that you provide, on the training process. And in deep learning, as you saw, there are many, many layers. And each layer is providing some kind of an information. And how do you extract this information? You extract this information, which is called feature maps, by applying what we call in computer vision filters. So each and every layer has a set of filters, what you see here. So you see that here, the filter is really, let's look at this filter. So we have here like a black line, white line, and another black line. So this is a filter which we apply to an image, and this filter travels on all the pixels of the image in a mathematical scheme that is called convolution, and it actually checks how this every single patch in the image, how much is it similar to this kind of information. So how much of behavior of black line, white line, black line exists in this patch. And this is really these are very basic features in images. So the first layer would give us information on very, very fine structures. Then the second layer, as you can see, we have a little bit more complex filters, which can be applied again on all the pixels of the image, and they will provide more complex information. And as we move further, what we see is that the filters are becoming more and more expressive. They are really becoming from very basic structures of lines, dots, etc. They are becoming more and more informative. So they can take the shape of person, of dogs. So you can imagine that when you look at the face of a dog, you don't really have to look at it at a pixel level. You can look at it like you can zoom out. And this is why we can learn so much from data and from images when we look at it from various scales, and we don't necessarily do all the analysis in one single scale, which is I would say the finer scale. We can really look at a very, very fine scale information to I would say, cursor scale information. And this is how things are working in a deep neural network. Now, a little bit of history. Lynette, so Yann LeCun, I don't know, maybe I hope you know this name. This is one of the godfathers of AI and deep learning. And Yann LeCun already in 1998, so 28 years ago, way before anyone I know thought that we will be using 28 years later AI and deep learning so intensively. So he designed Lynette. Lynette had a very important task to be able to read the zip codes on envelopes. And so the input was characters, probably numbers, and the output would be to actually say which character it is, and to automate, the tedious task of reading zip codes. So what Yann LeCun did back in 1998 was to have like a few convolutional layers. So we only deployed 4 layers of features, and then extracted a bunch of numbers. These numbers were, these are the fully connected layers, and they provided, I would say, let's say the last layer, if we want to find digits, then we had 0, 1, 2, 3, 4 until 9. And then you had a score for each digit. And the digit that got the highest score was the digit that was predicted by the neural network. And you can see here, this is, I think, from his website, Lynette working on an AT&T machine. And here you see the input, and you see the answer. So this so the neural network actually learned how to do that. And this was already 28 years ago. And then we had like not the Stone Age, but AI actually froze. It actually froze for many, many years. And then in 2012, some magic happened. And this magic was actually the result of 3 main things. The first thing was data, and the second thing was compute power, and the third thing was the ability to take the mathematics that was already there for several years, to use this data, exploit the compute power, and this was like the big boom for AI. And me as a computer vision person, I always like to mention the ImageNet challenge. This was a challenge where computer vision scientists would gather together in a conference in a very, very nice place and get a lot of images try to figure out what is the class of the image. Is it an airplane, a sheep, a dog, a cat, a snake, whatever? And this was his task, and the one who could find the algorithm which will give the best result got to be the winner and got, like fame at least for 1 year. And then in 2000, so this was going on for many years. And in 2012, something dramatic happened. The error, so this is the classification error. And this was the best, the winner, the classification error of the winner. And in 2012, the classification error reduced dramatically. Why? Because this was the first year where a deep learning-based solution was introduced to this competition. And also, I organize in Israel the largest computer vision conference. And in 2014, I can tell you, we had a session, it's a huge conference. We had one session on deep learning. And nowadays, in our latest conference, honestly, we had maybe 1, 2, 3 lectures that dealt with classical computer vision. Everybody is now doing AI because it's working unbelievably. But classical computer vision, I can tell you, still has a role. You really have to master both practices to create good algorithms. So back to 2012, what happened then? Alex Krizhevsky introduced AlexNet, and he won the first prize. And for the classification, he used a deep neural network. And you see that this is actually deeper from the neural network that Jan LeCun presented 14 years before. You have the image. All these numbers here are really telling us the size of the convolution filters which are deployed on this image. And we have a lot of steps. And finally, we have here a vector of 10,000 parameters. Each parameter symbolizes the probability that this would be any of 1,000 categories. So you can imagine that we have an image of a dog, and then we want that the parameter in this vector that is related to dogs will get the highest score. Okay, so it's quite simple. This is what we want. A picture of a dog, we want to have the highest score for a dog. And all of this thing here should assist us in doing that. And which we will try to figure out how it is done. And this is what we will try to focus on in the remaining of the hour. So we have several inputs. Something is happening in these inputs. We are having several layers and we get the output. So what are we actually doing? How do we make the prediction? So when we look at each and every component here, we want to look at the very, I would say, the basic component. We look at something which is also quite old, because I told you the mathematics was there. It was waiting for the opportunity. And so the mathematics here is the perceptron model, a very simple model. Even if you don't like mathematics, I guess all of you know how to do a weighted average, okay? So we have x1, x2, and x3. These are 3 numbers. Each of them has a weight, okay? So let's say it can be the number. This can be, I don't know, your grade, and the weight would be the number of students or the percentage of students that got this grade, and you want to calculate the weighted average of the grade of a class. Okay, this is something that we all know how to do. So if we want to have y, we will have the weighted average. So having several inputs, each of them having different weight, and calculating as the output the weighted average, this doesn't sound too complex, does it? Also, it doesn't sound very sophisticated. So what if you will have like a lot of these perceptrons connected to each other, does it make any sense? No, it doesn't make any sense. Because if we stick to just calculating linear weighted average, then if you will have a lot of these, what is a neural network? We just hook a lot of them together, then we will take a weighted average of a weighted average of a weighted average. It will be a very, 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 very long term, but it will be eventually a weighted average. And this will not give us something meaningful. But there's a small trick, and I think it's unbelievable how this small trick is making a huge difference. And this trick is the trick of nonlinearity. What do I mean? I mean that I go back to the same thing. I have here it's x0, x1, and x2, and we have the weights, and we are calculating again the weighted average. We are also allowing for some bias. It doesn't matter. It's not so important. But we are looking at what we got here, and we are asking ourselves, is this value large enough? If it's small comparing to some threshold, then it's not interesting for me. It is not contributing to my decision making. So this makes sense. If we have like some inputs coming, but they are not important, I don't want to account for them. Or I don't want to account for them at all. Only if they are above some threshold, then okay, I will introduce you to my decision-making scheme. And this, what we call activation function, really makes this a capability to make sophisticated models, because the features, all of these x1, x2, etc., these are features that we are generating in each and every layer of the neural network. But the neural network learns to which features it should account when it comes to solve a specific task. If we would have stayed in the linear model, then everybody would contribute all the time, and this would become meaningless. And this is a very, very important aspect of neural networks. Unbelievable. Just putting a threshold. And of course, we mathematicians, we like to make things complex. So why settle for one threshold when you can have a lot of thresholds? Each of them is like, a small tweak comparing to others. Nowadays, probably some of you heard of the ReLU, which is simply the max between 0 and x. So if x is negative, nobody cares about it. If it's positive, then you just get its value. So there are a lot of thresholds, and some of them, like the ReLU, are more commonly used in deep neural networks. That's great. So now we understand that in this mechanism where we have inputs, these inputs are, going, they are somehow weighted, and they are compared to some thresholding mechanism, and then they can travel to the next layer, go through the same process, and if they survive, they travel to the next layer, etc., etc. So this is basically the mechanism. But now let's try to go a little bit upper and take the view of the convolutional layers versus the fully connected layers. So let's start with the fully connected layers because they are a bit simpler. So the fully connected layers are usually layers of the decision making, and they are usually at the very end of a deep neural network. So usually they are like at the end where you really want to take all the information, use everything, and make the final decision. So assume that at a very late stage of the neural network, you have a set of, 1,000, 10, whatever inputs. You want to account for all of them. So each input has a weight. You have like the weighted sum or the weighted average, and then you are taking some kind of a step function, the threshold, and you get the results. So this is called the fully connected because you take all the inputs. And this is really happening in the very last stage of the decision making. I will skip this slide. It's not so interesting because I want to go to the convolutional part. Convolutions are one of the most important things in signal processing, image processing, mathematics. It's really one of the most important things. What are convolutions all about? So here is something, a nice gift that I really like. It's very relaxing. It can put you into a relaxed mood. Let me try to explain while you relax a bit. So let's say that you have here an image, and this guy is the filter that I mentioned before. Now, filter is really simply a matrix, which is much, much smaller than the image, and it has numbers. These numbers are the weights. Now, when this filter is traveling over the image, then what is happening that each time the center of the filter is centered around some pixel. And then what you have the multiplication of each of the values in the filters with the appropriate value of the pixel. So because you have like this mask, you put it on some centered on some pixel, and then each component in this filter falls on another pixel. You make multiplications, you sum it all together, and this is called convolution, and you put the new value here on the new image. Now, try to imagine that when you have different types of filters, you will get different responses. And you can detect things. We have, I would say, a method in classical image processing, which is called matched filters. You try to match between a filter and an image. So you look for phenomena in the image that resemble this filter. And the more resemblance that you have, the higher the values you will have as a result. So this is convolution. So try to imagine when I talk about features, I actually mean that I take different filters with different parameters, and I try to figure out what would be the result of applying this filter to an image. And these are exactly the features that I obtain. In classical image processing, these values, the weights, would have been fixed. By whom? By me, the developer. In deep neural networks, these values are learned by the neural network. And this is why it's data-driven, because the data impacts the training process, impacts the actual weights. And this is, I mean, this is amazing. This is really super amazing. Another, because the convolution, especially for people who didn't have the privilege to learn mathematics and don't like it even, I'm married to one. I'm the mother of two fantastic, beautiful, smart twin girls that really hate mathematics. So I really respect and love people who don't like mathematics. So here is another way. This is the original image, and you see that we have here really a calculation of multiplications and then summing it all, and this is what you get in convolutions. A very simple example that is used in computer vision is that of having the averaging filter. So we have here a filter which has a weight of 1/9, 1/9, 1/9. like a 3 by 3 filter. And when you apply this filter in a similar way that you saw here on an image, then what you will have is a blurred and more blurred version of the original image. Here is a question for you to think about. What happens if I deploy an average filter for infinity? What will happen? I will let you think about it. So the main conclusion up until now is that convolutions are a mathematical way to provide features, and these features are learned during the training process of a neural network. Okay. Another thing that you saw is that of subsampling. What we saw is that we start from the original size of the image, and then after we do here these convolutions, we extract features. Okay, then we have, so we have features which are on the size of the original image. But in the next step, we are looking at smaller images. What happens? How do we do that? So this process is called subsampling. And subsampling is also a very, very important issue in image and signal processing. It's very, very deep, and a lot of research has been done on that. So I'm not going to go into it. But to make it simple, I want to take this big image and I want to decrease it by a factor of 2. So what I can do very easily would be to take the max value in each and every 2 by 2 environment. This is one method. Another method could be take the average. Another method could be take the median, etc. Taking the max value is very common in deep learning. It even has a very fancy name, max pooling, but this is a way on how you can make your images smaller and smaller and smaller. And I think intuitively you can look at it as a way to really look at information by zooming out. Zooming out, so looking for larger and larger and more meaningful structures. Okay, so up until now, what we saw is how a deep neural network looks like, what are the main activities in a neural network, the layers, the perceptron, the decision-making, the threshold, the convolutional layers, the fully connected layers. And now the question that we have, and we will discuss it in the next session, is how do we make this neural network do what we want? Okay, we want it to do something. Okay, so we have the structure. Now let's understand how it is working. So for the next session, I will end this session with a teaser towards the second session. We will see that when we have our neural network, we have some kind of a prediction, and we have to compare it to the ground truth. This is why maybe some of you are contributing to the development of AI solutions by providing annotation. You are the oracle. You are the provider of the ground truth. Because if we don't have the ground truth, then for the classical deep neural network, we will not be able to assess how well the neural network is working. We will not be able to assess the error, and we will not be able to correct the weights of the neural network so that the loss, the error, will be reduced. So you were a fantastic audience. There were no questions in this session. I hope that everything was understood. I hope you saw that I really enjoy talking about these things. So this was the first step in our journey together to go from the very basics of deep neural networks to state-of-the-art. And I really, my aim and my hope is that by the end of all of these sessions that you will have a good idea of what is happening now, but also what it is based on. So we have reached the top of the hour. I really appreciate that you took the time to listen to me. Any comments, feedbacks, criticism? No, why criticize? But will be appreciated. Thank you so much. And thank you. Oh, Jacek, I think that I know you. I think that you are from Australia. Yes, there is a recording, and we will share the recording for everybody. So really, really happy to see here some old friends, and thank you guys. So I have to run, as I wrote in my LinkedIn today, I have to run to my gym to do some exercise. So thank you. Thank you so much. Looking forward to meeting you also next week. Ciao. Bye-bye.